So my name is Yolanda Nkalashe, and I form part of the Data Science for Social Impact, which is a group in the University of Pretoria. So I'll be talking about my work around interpretable natural language processing for classification of misinformation data. So I'll just take a step back in terms of the history and literature around explainability in machine learning. So the need for transparency and explainability, it all surrounds ethics, and I think that's why we're here today. So it's for users to be able to debug their machine learning models to detect failure points, especially in high-stake decision areas, ensure that your models are fair and do not have any bias, and to determine if a model is suitable for deployment. And for the most important part, it's for regulatory as well as ethical reasons. And this is how I've summarized in terms of how we can classify explainability in AI or machine learning. So I've classified interpretability in two classes, which is self-explaining or white box model, as well as post hoc interpretability. And both these can be further classified into global or local interpretability. And then the techniques to achieve these interpretability is you can have your intrinsic interpretability, model agnostic, model specific, and example based. And the focus for today will be example based interpretability. And I'll discuss in terms of what my research aim is. So our research aim is to achieve explainability in natural language processing models, given that natural language processing tasks are complex in nature. So we would like to see if we can't achieve desired accuracy whilst being able to explain our models. So we want to answer three crucial questions. We want to find out if we can use prototype selection to interpret how a classifier predicts misinformation tasks. We want to identify what linguistic properties are considered when classifying, and if we can build a disinformation unsupervised classifier using prototype selection methodology as a clustering technique for interpretability. So just to give a background around example-based techniques. So example-based techniques aim to human understanding. So they focus in terms of a normal human, how they would interpret an image, a text, etc. Because there's evidence from psychology which indicates that humans usually understand complex scenarios by using examples. So how we do that is we select a small sample of our data representation, which represents our data set. So we select a small sample from our data, which are the best representatives of our full data set. So these example-based techniques include your influential instances, advisory example, counterfactual examples, and prototype selection. Our focus is prototype selection and how we can use that on classification of misinformation data. So prototype methodology seeks to extract a minimal subset of data that can serve as a representative of the data, such that users can get insights from the data to understand how the model will make its decision. However, together with prototypes, we also need to have outliers from the data set because we need to represent the data set in its holistic view. So we also extract criticism. So criticisms are data points which don't fully represent the data. So in essence, our outliers. So this is just a graphical view, which was sourced from the book called Interpretable Machine Learning, which shows in terms of these data points, where criticism lie and where your prototypes would lie. So I'll take you guys through a step-by-step in terms of how we select our prototypes from our data set, and this will be focused on the natural language processing data, which I extracted from Kaggle. So this is the methodology, right? So the methodology uses our maximum mean discrepancy in order to select our prototypes. So we start off with an empty list. And while the number of prototypes is below the chosen number M, so you can either choose the number of prototypes M, or you could set a threshold in your algorithm saying that once your MMD has reached this specific threshold, you can stop the algorithm. So in our case, in our experiment, we chose the number of prototypes M. So once, while the number of prototypes is below a chosen number, so this is how your data set will look after you've encoded your text and after pre-processing. Then you select a specific, so it will run through all the data points. So it will select a data point and check how much the MMD is reduced when the point is added to the list of prototypes. If it is reduced enough, then it will be added to the prototype list, else it will be rejected to be added to the prototype list. And then once you've completed this whole iterative process, this is the output. It will output a weight and also the index in terms of where this prototype lies in your whole data set. And then this is how you can convert it back and decode it back into text, basically. So this is just an insight in terms of how the algorithm runs and how the MMD works. So I'll take you a step back and explain how we did our pre-processing and the data set that we've used. So the data set that we used was a Kaggle misinformation data set. So it was an ISA data set. So it spoke mostly around your politics in terms of US. The total size was around 38,000, with 17,000 being fake news and 20,000 being labeled true. So we just focused on the text column, and we did not look at the title or subject column. And then before selecting our prototypes, we tokenized our data using the BERT tokenizer. And once all the data was pre-processed and clean, so how we pre-processed our data. So we did not lower our data because we did not want to lose any linguistic properties. However, we did remove some of punctuation marks as well as the most common words that were found. And then in our initial experiments, we chose M to be 30, 40, and 60. And this was the initial insights that we got from our data set from the prototypes. So what we found is that most of the fake news will use a lot of the strong languages. It will have a lot of words which are mostly capital, as well as it will have a lot of exclamation use in its text. And then what we further did is we also focused on part of speech tagging as well as sentiment in terms of facts and opinions, as well as negative and positive. And then this graph basically shows, so the green dots are the fake news prototypes, whilst the pink is the true news prototypes. So from this graph, what we basically got is that most of the time we can see that our pink dots, a lot of our pink dots are in this quadrant, which means that they are positive and also they speak around the facts. Whilst most of our fake news lie in this quadrant, which it's also positive, however, it's mostly under opinions. And then from our part of speech tagging, what was quite significantly different between our true values and our fake values was that a lot of our fake news uses pronouns. They have a lot of punctuation use and also other, as well as spaces, which is used in the text, which is something, an assumption which we also made before we started the experiment. And then what we further did is we used the Centerval toolkit. So the Centerval toolkit helps you to probe into an embedding to indicate what linguistic properties actually lie within that embedding. So we used that toolkit in our prototype embedding. So we also used a BERT embedding, but we used this toolkit before the model was trained. So it was the pre-embedding. And this is what we found as well in terms of the probing techniques that we used. We used cent length, which is the length prediction, the tense, which is verb tense prediction as reshift, which is word order analysis. So with sentient, what we found is that the fake news is usually short in sentences, whilst true news, we usually have lengthy sentences. And then in both cases, we had high accuracy for tense as well as word order analysis, which means that those two linguistic properties are very crucial in terms of predicting whether a text is true or fake. And we also took it a further step in using our prototypes as a nearest neighbor classifier and compared these results with a BERT classification result. So what we found is that in this graph, it shows the test error of the cluster, which is the nearest neighbor classifier using our prototypes, as well as the test error for BERT. So we found that the test error is slightly higher in terms of when we're using the nearest neighbor classifier, but we're also assuming it's because we just sampled a few prototypes. So we're hoping that as we increase the number of prototypes that we select from our data set, because in the paper that we read, they selected around 4,000 prototypes. So we're aiming to also select that number of prototypes, and we're hoping that when we reach that number of prototypes, our test error will be as small as that of BERT, which is one of the good classifiers in essence for NLP. So our future work from here on is to see post-training in terms of what our embeddings have and what linguistic properties are captured during training, to get further insights on our critics, and to see what different insight can we get from a South African context misclassification data set. So so far we've extracted the COVID-19 misclassification data set, which we're currently working on to see if we can get the same insights in terms of the prototypes which we have selected.